Right now, at this exact moment, there are two machines operating in interstellar space. Not one, two. Most people know about Voyager 1, the farthest human-made object ever built. The spacecraft that famously crossed into interstellar space in 2012 and has been sending back data from the dark ever since. It is the one with the golden record, the one that routinely makes headlines, the one that defines our understanding of the deep unknown. But there is a second spacecraft out there. It is quieter, less celebrated, and moving through the void 13 billion miles from Earth in a completely different direction. It is sampling a completely different region of interstellar space. And it is carrying a specific piece of technology that Voyager 1 lost decades ago. A piece of technology that turned out to be the single most important instrument for understanding what actually lies at the edge of our solar system. It is called Voyager 2. And what it found when it crossed into interstellar space did not just confirm what its twin discovered, it contradicted it, it complicated it. It raised fundamental questions that Voyager 1 simply could not answer, because Voyager 1 was literally blind to the most critical aspect of the boundary between our solar system and the rest of the galaxy. Voyager 2 was not. And right now, in the summer of 2026, Voyager 2 is about to become the absolute center of this mission, not just because of what it discovered, but because of what is about to happen to it. A procedure so risky, so completely unprecedented in its design, that the engineering team calls it the Big Bang. A simultaneous, all-or-nothing reconfiguration of every remaining power system on the spacecraft, attempted across a communication delay of more than 16 hours each way. There is no backup plan. There is no second attempt. If it works, Voyager 2 buys itself more time. If it fails, the map of the interstellar medium stops updating. You're watching Beyond the Signal, where we follow the evidence to the edge of what science knows. To understand why this moment matters so much, we have to go back to the beginning. Voyager 2 launched on the 20th of August, 1977. That was 16 days before Voyager 1. The numbering is not a mistake. It reflects the order in which the two spacecraft were expected to reach their primary targets. Voyager 1 was put on a faster track. It was aimed at a trajectory that would take it past Jupiter and Saturn, and then angle it upward, out of the plane of the planets, accelerating quickly toward interstellar space. Voyager 2 was given a different assignment. It took a longer, much more complex route. A route that allowed it to do something no other spacecraft had ever done, and nearly 50 years later, no other spacecraft has repeated. Voyager 2 is the only machine in human history to have visited all four of the outer planets: Jupiter, Saturn, Uranus. Neptune, every single gas and ice giant in our solar neighborhood, observed up close. Voyager 1 sacrificed Uranus and Neptune to get a closer look at Saturn's massive moon, Titan, and to reach interstellar space faster. It was a deliberate choice by mission planners. Two spacecraft. Two different answers to the question of what the outer solar system looks like. But the price Voyager 2 paid for that grand tour was time. Its trajectory was shaped by the gravitational assistance of four different planets, which slowed its outward progress compared to its twin. Voyager 1 crossed the Heliopause in August 2012. Voyager 2 did not cross it until November 2018. That is a gap of more than 6 years. For 6 years, Voyager 1 was already out there, measuring the magnetic fields and cosmic rays beyond the boundary, sending back data that was actively confounding researchers and forcing them to reconsider their models. For 6 years, the data told us that something extraordinary was happening at the edge of the sun's influence. But the story was incomplete, because of a failure that happened a long time ago. Here is the part most headlines miss when they talk about the historic crossing of Voyager 1. Its plasma science instrument stopped working in 1980. This was the device specifically designed to directly measure the temperature, density, and flow of plasma. Plasma is the superheated gas that makes up the solar wind and fills the space between stars. That instrument failed before Voyager 1 even reached Saturn, 4 decades before it reached the Heliopause. This meant that when Voyager 1 finally crossed the boundary in 2012, it did so without the ability to directly measure the plasma on either side. Scientists had to infer what was happening. They looked at data from the cosmic ray detector and the magnetometer, and they pieced together an educated guess. They were working around a blind spot, a gap in the data that had existed for 32 years. They could not fill it, but Voyager 2's plasma instrument was still working. When Voyager 2 finally reached the Heliopause in late 2018, it was carrying the exact sensor that its twin had lost. And at that boundary, it produced a dataset that researchers immediately recognized as historic. It was the first direct measurement of plasma on both sides of the Heliopause, taken simultaneously as the spacecraft physically crossed the line. In November 2019, 5 separate papers were published in the journal Nature Astronomy detailing exactly what those instruments found. What they found contradicted the existing models in ways that genuinely shocked a scientific community that had been relying on Voyager 1's incomplete picture. The first major surprise was the structure of the boundary itself. Scientists expected the heliopause to be a relatively sharp transition, a defined wall where the outward pressure of the solar wind meets the inward pressure of interstellar space. Models predicted a narrow zone, maybe a few 100,000 miles wide, where the two environments met and blended. What Voyager 2 found was not a wall. It was a distinct transition zone roughly 100 million miles wide, and it was sitting just outside the heliopause, out in what was supposed to be pure interstellar space. Instead of a clean break, Voyager 2 detected a region where interstellar particles had pushed inward, like tree roots cracking through concrete. Tendrils of interstellar material were extending millions of miles inward, mixing with the solar environment in a way the physics models did not predict. Voyager 1 had seen something somewhat similar, but on the inside. Before crossing, Voyager 1 found a stagnant zone where the solar wind essentially ran out of momentum and stopped moving outward. Voyager 2, approaching from a different direction years later, saw a completely different structure. 2 spacecraft, 2 crossings, completely different boundary behaviors. Put that into perspective. Dr. Stamatios Krimigis, the principal investigator for the low-energy charged particle instrument, pointed out a contradiction that is still being debated today. Both probes encountered the heliopause at almost exactly the same distance from the Sunday. Voyager 1 crossed at 121.6 astronomical units. Voyager 2 crossed at 119 astronomical units. That sounds consistent until you realize when they crossed. Voyager 1 crossed near solar maximum when the sun was highly active and the solar wind was blowing hard. Voyager 2 crossed near solar minimum when the sun was quiet. The heliosphere is essentially a balloon inflated by the solar wind. It should expand during solar maximum and shrink during solar minimum. But both probes found the boundary sitting at basically the same distance. The balloon did not shrink. When asked why, Krimigis stated plainly that we do not understand why. That is a profound admission from a senior scientist. It means something fundamental about how our sun interacts with the galaxy is missing from our understanding. Then came the second surprise: the temperature and the density of the space between stars. The plasma inside our solar system, carried outward by the solar wind, is incredibly hot. In plasma physics, temperature is a measure of how fast particles are moving, not how it would feel to human skin. Scientists expected that when the plasma crossed the boundary into interstellar space, it would hit a much colder, denser environment. Voyager 2 measured this transition directly. The temperature drop was sharp, but what happened to the density was staggering. Both spacecraft confirmed that the space between stars is not empty. It is filled with plasma that is more than 40 times denser than the solar wind at the edge of the heliosphere. Voyager 2's working instrument finally gave us the temperature of that interstellar plasma. It was between 30,000 and 50,000 degrees Kelvin. That sounds incredibly hot to us, but it is actually far cooler than the millions of degrees measured just inside the boundary. For the first time, scientists had a real number, a baseline measurement taken directly from the interstellar medium. Prior estimates, based purely on theory, had been off by a factor of 2. But the third discovery was perhaps the most unsettling. The heliopause leaks. It is not a clean border. It is a highly porous membrane. Particles cross it in both directions. Voyager 1 saw interstellar particles punching inward. Voyager 2, approaching from the south, saw low-energy solar particles leaking outward. They were escaping into interstellar space before the spacecraft had even reached the boundary line. This was not a localized fluke. It was confirmed from 2 different entry points at different times in the solar cycle. The boundary behaves less like a solid wall and more like a rugged coastline, with the surf washing in and out, mixing the waters of 2 massive oceans. Ed Stone, the legendary project scientist for the Voyager mission, said the probes are showing us how our sun interacts with the stuff that fills the galaxy. Notice the phrasing. Not where the sun ends. How it interacts? It is a messy, dynamic, ongoing relationship. And even today, billions of miles past the boundary, both spacecraft are still flying through a transitional region. They have not yet reached completely undisturbed interstellar space. Now look at what happens next. The reality of operating a spacecraft launched in 1977. Voyager 2 currently has 3 operating science instruments: the plasma instrument, the magnetometer, and the plasma wave subsystem. Working together, they provide the only continuous, real-time measurement of the interstellar medium in existence. But the power is dying. Both Voyager probes are powered by radioisotope thermoelectric generators. They run on the heat produced by the decay of plutonium-238. That decay is a mathematical certainty. It cannot be stopped, paused, or reversed. Every single year, Voyager 2 loses about 4 watts of available electrical power. At launch, it had 470 watts. Today, it is running on the absolute margins. Voyager 2 actually has slightly more power left than Voyager 1, which is why it can still run 3 instruments. But that margin is shrinking fast. This brings us to the summer of 2026, the Big Bang. NASA engineers at the Jet Propulsion Laboratory are forced to execute a maneuver that goes against every standard protocol of spacecraft management. Normally, when you change a power configuration on a deep space probe, you do it one switch at a time. You send a command, you wait for the telemetry, you verify the state, you move to the next switch. You cannot do that anymore with Voyager 2. During any power transition, there are moments where systems draw unpredictable amounts of current. If the spacecraft's automated fault protection system detects a power draw that exceeds what the decaying generators can provide, it will assume a catastrophic failure is occurring. It will autonomously start shutting down systems to save itself. Once it shuts down a science instrument in the freezing cold of deep space, you likely can never turn it back on. To avoid triggering that automated defense, the engineering team has designed a procedure to bypass the intermediate states entirely. They are swapping out a group of powered devices all at once, shutting down old configurations and bringing up lower power alternatives simultaneously. A complete restructuring of how power flows through the spacecraft, executed in a single moment. Think about what that requires. Every command sent from Earth takes over 16 hours traveling at the speed of light just to reach the antenna on Voyager 2. It takes another 16 hours for the spacecraft's confirmation to reach the Deep Space Network antennas back on Earth. More than a full day passes between pushing the button and knowing if you just killed the most important probe in interstellar space. If the Big Bang works, it recovers enough wattage to keep the science instruments alive for at least another year, maybe more. And if it works on Voyager 2, they will attempt the same maneuver on Voyager 1 shortly after. Voyager 2 goes first simply because it is slightly closer and has a slightly better power margin. It is the test subject for the survival of the entire mission. What is at stake here is not just the lifespan of a machine, it is the continuation of human knowledge. The shape of the heliosphere is still unknown. Some models say it looks like a comet with a long tail, others say it looks like a deflated sphere or a croissant. Voyager 1 and 2 are our only points of reference. Their magnetometer data is currently mapping the local interstellar magnetic field, which tells us how our entire solar system is oriented relative to the Milky Way. When these two spacecraft finally lose power, and they will, there is no replacement. There is no backup probe currently flying through the Kuiper Belt. There is no funded mission ready to launch tomorrow. When Voyager 1 and Voyager 2 go dark, our live feed from interstellar space cuts out. The map stops updating. For decades. The people keeping these machines alive are a small group at JPL. They are working with coding languages and engineering philosophies that predate modern computer science. It is an institutional knowledge that exists only in their heads and in fading manuals. They are managing the slow, graceful death of two machines that were designed to last 4 years and have survived for nearly 50. Voyager 2 was the twin that took the long way around. It showed us the ice giants. It found moons we didn't know existed. It proved that Europa might have an ocean beneath its ice. And then, it pushed through the boundary of our solar system, carrying the one instrument capable of telling us what the space between the stars actually feels like. We are waiting for the signal to confirm the results of the Big Bang maneuver. The signal is still moving through the dark. It is still coming. If you want to follow the actual data from the edge of space and understand what the final days of the Voyager mission will reveal, subscribe and turn on notifications. Tell me in the comments which part of Voyager 2's journey surprised you the most. This is Beyond the Signal. Keep looking past the obvious.